times U effective squared times the log of lambda over EF plus some constant. Okay? So there's a hidden dependence here of lambda naught on where I chose to define my field theory. It's a very gentle dependence. It only depends logarithmically on this. But if I plug that in here, this becomes this.
Proportionality, not equality.
Some constant.
Yeah, if you want.
Correct. It's a proportionality.
But that, in some sense, from general perspective, implies that you could start RG from the scale order of EF.
Well, but I don't actually know how to do RG there. And so for this problem...
Well, you can linearize your dispersion.
Right. For this problem, it's a trivial distinction. But when we go to the repulsive U Hubbard model, we're going to discover that this is a very important distinction.
But haven't you actually done this RG from the EF scale?
No. No, I've done something very different. I've integrated out everything in one block. And so, whereas here in this RG, all that comes in are Fermi velocities, for instance, so that this RG equation doesn't depend on scale at all. In fact, for a general band structure, the interactions depend in complicated ways on the band structure. And I've managed to lump all of that into one step. That all went into chi, for instance. Let me make one final comment here. Let's ask what happens in case 2. In case 2, where we have two types of interactions, one of which are instantaneous and the other are retarded. And let's ask what happens here in step 3. We went through to the end of step 2. But here what we find is that there are two sorts of G's. There's G, which depends on U, and there's G tilde, which is the retarded interaction that depended on the electron-phonon coupling. But now, since considering a diagram like this, if this is a G tilde, if this guy is at 0 frequency, it's on the Fermi surface, and this guy is supposed to be fast out at the cutoff, then this interaction has to transfer an amount of energy equals to the difference in energy between these two. Which means that as long as lambda prime is much bigger than omega naught, then G tilde does not renormalize. So the RG equations become dG dL equals minus G dot G, as they were before, and dG tilde dL equals 0. In this case, G just comes from the Hubbard model, so it's purely repulsive. So this scales to smaller and smaller values under a normalization. Rho of EF times U goes to rho of EF times U over 1 plus rho of EF times U times the log of lambda prime over lambda. Well, actually, E Fermi over lambda, lambda prime over E Fermi, if I do all of my fancy tricks. But the retarded interaction doesn't change. So we do these integrations until we reach another scale that's important. Now it's a physical scale. When lambda prime equals omega naught, now suddenly we're back to case 1. Now my new bandwidth is smaller than omega naught. So now I take a new effective lambda, which is equal to the renormalized repulsion, which is called mu star, minus lambda naught, the electron-phonon coupling, I guess that's alpha squared over 2k. And now I do step 4, which is the same as step 3 was in the original electron-phonon coupling, in case 1, thank you, leaving me with Tc equals equals omega naught now